Hello everyone, I'm Hassan, a PhD student at UC Davis. Amit couldn't show up today, so he asked me to give the presentation, so I hope he does not regret this decision. So, before I start, I need to mention that this project, a lot of people have been working on this project, a very huge team as you can see. So at UC Davis, my advisor, Amit, me, Thomas, who was a previous postdoc and now a faculty in Poland, Vince, a previous postdoc also, and now a faculty at Sandia Labs, Forel Assessor, Mason Walters, Ali Bomba, UC Irvine, Farzin Zarian, and Pablo, who is now faculty at Ecuador, Brigham Young, Paul Richards, and lately UCL, Carmine Galasso, and Biao Song student. As acknowledgements would get lost at the end, I would like to acknowledge the sponsors. So, first of all, here, an AISC and Charles Pankow Foundation, and also the California Strong Motion of Instrumentation. So, just an overview about what we're doing here. So, see, moment frames are important in general, right? But in the specific talk today for transportation structures, it's more related to airports, where every single airport across the US would have a steam moment resisting frame. Our focus is on the base connection. So we think that base connections haven't got that much attention in research as compared to other connections, for example, beam column connections. So we do not design this base connection optimally, and we end up not designing the frame optimally also. So we have this knowledge gaps about how this interaction goes on between the base and the frame, which is really an important issue. So just a quick overview also of how these connections are designed in practice. So these connections are designed as capacity design. So you design it to be stronger than the column in order to form the plastic hinge in the column, not in the base itself. So you end up getting this huge base plates, which sometimes end up like being unreasonable in order to satisfy this check of 1.1 RY and P. And it even gets more complicated when you start dealing with larger columns. So practitioners end up embedding the whole column into the concrete in order to get more resistance, which would end up with this pretty absurd connection, which this part is only the embedded part in the concrete. So also interestingly, our tests for base connection designs, the data we have showed that these connections are pretty ductile, so you could reach up to 5%, 6% rotation capacity. Which more interestingly, research on columns itself have shown that you get this twisting and lateral torsional buckling, local buckling issues way before you reach such rotation capacities. So we are kind of protecting the more ductile elements by designing it to be stronger than the column, which also end up being like very expensive and problematic. So if I just have to break down the entire area or body of work, first we wanted to come up with a design paradigm of how to design weak bases and to see its implications on the frame performance. So first part of the project, or like major part of funding for this project coming from AISC and Charles Pankow Foundation, is going towards the experimental testing, the component testing. So we are testing reliability ductile details, and we are testing some embedded also details. And then the peer part of the project is to look at the frame analysis. So we want to look to the component models we got from our tests and to apply it into frame simulations to see how this affects the stiffness and strength of the frame, and also what are the deformation characteristics of the base we're expecting. Also, we end up having some more funding from Smith just to validate or benchmark our models against some of the instrumental buildings. So when I show the outcomes here, which is pretty nice actually, by the way, if you think of it. So we end up having this design methodology of designing bases to be weaker than the column. We also have more data about the untested details that we know no knowledge about it. And also we were, like, the ultimate goal for this study would be to shoot for the code changes. AISC 341 and Design Guide 1, which is used to design these base plates. This is how we started, but then lately we got even 2 more projects added to this fairly comprehensive study about base plates, where we have one project going on with Hilti to study the biaxial bending effect of these column bases. Also, this collaborative project with UCL for studying the reliability of these connections, which is also adding to our outputs to produce hopefully a strength model for designing biaxial bending exposed base connections, and to calibrate our resistance factor which is used in the code. I'll be mainly talking about the peer part of the project because it's a peer meeting. I will also go through our progress throughout the whole every project of these briefly, if the time allows. So the peer part mainly was, as I said, to look at the analysis of the frame itself using the models that we got from experimental data. So first, development and creating these models, calibrate the models, and then use them in the frames to see how they interact or what are the implications on the performance and the collapse of the frame. And then we go back and inform for the experiments, so that if we need to test certain details in order to kind of loop back and check it again, that will give us great insights. And at the end, perform this design examples and code changes. So first part, the component models. So we've been looking into embedded and exposed base connection throughout I think the 10 past years. We came up with models that are calibrated and against the experimental data we had. And if you look at the figure here, it's just how this connection behaves. You get this hysteresis of flag shape, which tends to recenter back. So we kind of developed models with parameters and modes that accurately captures this behavior. And then we got lucky that we could use this SMIP study I mentioned before to validate and benchmark our models, which, if you look here, it seems to be tracing the response we got from the instruments better than what we actually do in practice. So in practice, you just assume it's fixed or hinged. So the model actually shows the least error out of these 2 assumptions, which is pretty good also. Next step was to take these models and put it into frames and then run analysis for the frame itself. So we ran a parametric analysis, parametric simulations for frames ranging from 4 to 20-story buildings. Each of the buildings had the base modeled as I mentioned before, referring to the models we developed. And we ran a FEMA P695 type analysis to check the performance of the frame and the probability of failure, varying two main parameters. First, the strength of the base, where we designed the base for different strength scenarios, and we also varied the rotation capacity of the base. So first, let me talk about the strength. So one of the scenarios we used was the current practice, which is designing the base for 1.1 RYMP, and the other scenario was designing the base for R=8, which is how you design the beam column connection, for example. And we designed also a scenario for R=3, where how you design structures that are not very ductile according to the code. And the final one was designing the base for an overstrength seismic load, ω0=3. I will be showing only the results from the last one, which is the most promising, ω0=3. And turns out that designing the base for ω0=3 overstrength seismic load is actually cutting down the base moments by half and sometimes 3 times for higher story buildings. So to explain just this graphic, so what you see on the y-axis is the probability of failure, and plotted again is the buildings with different stories, and the bars here in the histogram represent the rotation capacity we varied. So as you see, it varies from 1% rotation capacity at the base to 5% and then to like infinite capacity. This graph, as I said, is representing the cases when we designed it for ω0=3. And it's really interesting if you look first at the 4-story building. With this red line is presenting the probability of failure of 10%, which is the range where the design practice is currently using. So actually there is no difference if you design it for 1.1 RYMP and ω0=3 with this reduction in the moment, and then you get the same performance. And this is mainly because for the 4-story building, the collapse is, the failure is dominated or governed by the sideway collapse rather than deforming or having inelastic deformation in the base. And then when you look at the 12 and 20-story buildings, you get actually, like we could say, fighting results, or results that could be comparable to the required probability of failure. I think all of them below 20% or 80%, if you can guarantee that the base would have 5% rotation capacity, which is interestingly really easy based on the data we have. Without any special detailing for ductility, we get 5–6% of rotation capacity. So this is a huge reduction in the moment and then reduction in the cost of designing these connections. And then next for the fun part, for the experiments, we've been